Okay, so I want to do 11.5, checkpoint 11.5. Let me go into OneNote. Okay, so it says, starting from a position with rotational coordinate 0, an object moves in the positive theta direction at a constant speed of 3 meters per second along the perimeter of a circle of radius 2 meters. What is the object's rotational coordinate after 1.5 seconds? Okay, so how are we going to solve this? Let's just write down a few things that we know. Well, we know that the rotational coordinate is given by S over R. That's your arc length. And R is your radius. We are given that the velocity is 3 meters per second. We're told that the radius is 2 meters. And we're told that this object is moving for 1.5 seconds. 1.5 seconds. Okay. So now, let's try to draw something. Let's assume they don't give it to us, but let's assume counterclockwise as positive. Okay, and let's assume that that is our rotational coordinate equal to 0, and it moves around, moves like this. We don't know how far it's moving, but it moves like that. Okay, so the velocity is 3 meters. Now, when we talk about the velocity, remember we're talking about the velocity of the object that's always tangent to the curve. So at any point, you draw a dot and you draw a tangent line and an arrow. That is referring to the velocity. As remember that it's changing the whole time. And remember, if we're talking about the velocity is related to the arc length. Okay, the arc length. Meaning that if we want to know the distance that the arc length, or the change in the arc length, if we've got time and we've got velocity, we can calculate this arc length. Okay? So remember that velocity, I'm just doing it in a very crude way here. Velocity is your x over t, right? Or delta x over delta t. It's your change in position. And actually, when it comes to moving in around a circle, this will be your delta s. Okay? Because your velocity is your arc length, your change in arc length over change in time. So if we've got velocity and we've got time, we can calculate our s. So our delta s is equal then to velocity times time. So our velocity is given by 3 meters per second. Our time is 1.5. So this equals 4.5 meters. So what does this mean? It means that starting from this 0 coordinate and moving at 3 meters per second around the circumference, after 1.5 seconds, we've traveled 4.5 meters along the circumference. That's my arc length. Okay? But now, by the way, I don't have any feel for where I should draw this. I'm just giving you an idea. But now our rotational coordinate is s over r, so it's 4.5 divided by the radius of 2, which is 2.25. Okay? But still, I don't really have a feel for what this means. And I just want to add this because I think this helps me a lot. What is 2.25 in terms of rotational coordinate? Well, the way that I like to look at this is I like to relate this to a complete revolution. Okay, so remember what we said earlier in the previous video was that if we divide this guy by 2 pi, if we divide theta by 2 pi, which is 2.25 divided by 2 pi, we get 0.36 approximately. So what does this mean? This helps me understand this a lot easier. Of course, this was the answer, right? So if you got this, that's good. But in order to relate this to my understanding of circular motion, what this is telling me is that this coordinate, if measured from 0, I've moved 0.36% of a complete revolution, right? So it's more than a quarter, and it's not a half. So what would 25% be? It would be you move from there to there, right? What would 50% be? It would be you move from there to there. 75% is 3/4, and 100% means you've gone all the way. Okay? And so remember, also, if you want to know what the degrees are, you multiply this by that 0.36 times 360 degrees, and we get what? 0.36 times 360, if I didn't make a mistake, is about 129.6 degrees. Just check me on that if I didn't make a mistake. 0.36 times 360, 129.6 degrees. So we know that that's 90. That's 90 degrees, and that's 180 degrees. So 129 is kind of somewhere there, right? So actually 4.5 meters was there. That rotational coordinate from there to there is 2.25. In degrees, it's 129.6. In terms of revolutions, it's 0.36. So I hope you guys are getting the idea. Just play around with this a bit to kind of get the idea. Okay, this is turning out to be a long one, but I hope this is helping. B says, how long does it take the object to complete one revolution? Okay, so using this technique of mine, we know that, first of all, your period is how long it takes to complete one revolution. So it's going to be delta t over the percentage of a revolution. Okay? Or it's simply, if you travel through one revolution, how long does it take you to travel through one revolution? So I've got, in the top here, the only time I've got is, I've got 1.5 seconds. But now I want to know how much of a revolution did I pass through in 1.5 seconds. And that's it there. It's 0.36 of a revolution. Okay? So it took me 1.5 seconds. It took me 1.5 seconds to move from there to there, to move 4.5 meters, to change my coordinate 2.25, to move through 129.6 degrees, to move through 0.36 of a revolution. So if I do this, then I get approximately 4.2 seconds. Okay? So that is the way that I would do it. I think there is a different way in the back of the textbook, which is 100% correct. So you can use both ways. And then what is question C? What does question C say? What is the rotational coordinate 1 second after passing a point on the circle whose polar angle is 90? Okay, so let's draw this again. There's 0, okay? And we know that that's our polar angle of 90, okay? The object's there. But now it says 1 second after passing this point. 1 second after passing this point. So we already know that if you've traveled 90 degrees divided by 360 degrees gives me 0.25 of a revolution. 0.25 of a revolution. So if I want to know what my rotational coordinate is, I can say 0.25 times 2 pi. Okay? And I think that gives me about 1.57. Okay, but now it's traveled another 1 second past this. Okay, I don't know where it stops. I'm not sure where it stops. So if we know that it's going at 3 meters per second and it travels for 1 second, then we know that our arc length, this arc length, is equal to, remember, Vt. Remember, V is s over t. Velocity is distance over time. So s, arc length, is that velocity times time. So that's 3 meters. So it travels another arc length of 3 meters past 90 degrees. So we're looking for, what's the question? I think we're looking for this guy. So what is our delta theta from that point to that point? Well, we know that delta S, this is R, delta S is 3, R is 2, so this is 1.5. So the delta theta from that point to that point is 1.5. But we need to add that onto that. So the total delta theta is 1.57, which is this one, from there to there, plus 1.5 is 3.07. Okay? Now what happens, so that's its final position, is 3.07. But remember what I always like to do, that's the answer. What I like to do is to convert it into a percentage of a revolution or into angle, just so that I know where I am on the circle. So 3.07, if I divide 3.07 by 2 pi, I'm effectively dividing it by a full revolution. So if I take 3.07 divided by 2 pi, I get 0.488 or 489. So what is this telling me? It's telling me that I've almost traveled 50% of the circle. Okay, as you can see, it's right there. And now, if I multiply this 0.488 by 360, I get 175.9 degrees, which you will agree, it all makes sense. If that is 180, then if I'm just short of that, I'm going to get 175.9. So all of these are different ways of looking at this. Okay, I hope that helps. Cheers.